Unlike the previous two examples where the values for your x and y are very clear, this time we are not given with that yet, but we are given here that this given integral for our contour or smooth path C is bounded by y is equal to x squared and y squared is equal to x. In order for us to solve for this using the Green's theorem, which allows us to use the double integral along that given region, and then you have here the partial derivative of your q function with respect to x minus the partial derivative of your p with respect to y dx over dy. We need the appropriate boundaries for your x and y. So that also we need to decide which would be preferred first, whether it would be the integral with respect to x or with respect to y. Now, in order for us to identify that, the thing that we need to understand here is that our region is bounded by this. If we're going to come up with a Cartesian plane, just allow me to draw a raw form here for the Cartesian plane here. We know that our y is equal to x squared is a parabolic curve, okay, from here, and then it will go up. It passes to the origin at 0, 0. But for our identified second function, which is y is equal to, or y squared rather, is equal to x, it's actually a parabolic curve as well, but it opens to your right. It's actually in this form here. It would be in this form somewhere here. I'm just gonna assume, assume that my graph here is appropriate. The point here is that the region identified here is this region here bounded by the two curves. Okay? So the point here is we need to identify the boundary for your x and for your y, and therefore us to identify here the integral for our each of the integral sign. Now, to identify that, of course, we can use here systems of equation. We have here y is equal to x squared, and you have here y squared is equal to x. In short, if we're going to substitute that here, y is equal to, your x is actually y squared squared, meaning y is equal to y to the power of 4. Solving for y, you will have here y to the power of 4 minus y is equal to 0. That would mean your y, if we're going to factor that, y cubed minus 1 equal to 0. What would be the values of your y? It would be y is equal to 0 and y cubed minus 1, okay, is equal to 0, or y cubed is equal to 1. Y cubed or y based on that is just equal to 1 here. So you have two values for your y, 0 and then 1. Using that in any of the given equations here, let's say this one here, or since it's y, let's use that here. So for y is equal to 0, our x is also equal to 0. The first point is at 0, 0. When y is equal to 1, 1 squared, you also have 1 and 1. In short, this point of intersection here is clearly at 1 and 1. And of course, you start here 0 to 0. So what would be the values? Sorry, this is 1 and 1. What would be the values for your x and y? Now, looking into this perspective, you can of course say that your y changes from 0 to 1 together with your x, 0 to 1. But since our given figure here is not a rectangle nor a square, it's a boundary, or it's a region bounded by those two curves, we cannot actually assume those perspectives. But what we can do here is this. Allow me to discuss this in this manner. Your x is actually between 0 and 1. However, based on your given here, your y is between x squared, and if we're going to solve for y for this, y is actually equal to the square root of x. So it's between x squared and square root of x. Okay? So whatever will be the value of your x, y is between those two functions. Now, why is it that x square root of x is the upper boundary for y instead of x squared? Because if we're going to look at this Cartesian plane, as you move down or go up, the upper boundary, or the graph that is the upper boundary of this region, is this equation here. y squared is equal to x. The lower boundary, the red one, is this one here. Hence, we can see that this is really the correct region for your x and y. Now, we can see here that our x is simple. Okay? It's 0 to 1. But our y is expressed as two functions, x squared and then square root of x. What is the point of this discussion? This means that if we are going to prove or show this item here, okay, as we're going to solve the value of this given expression using the Green's theorem, we are going to use, yes, the perspective to use this dy first before dx, so that as soon as you apply dy, it would be expressed as x squared or square root of x. Then later on, we can actually use the value for our x between 0 and 1. Because if we're going to start with dx, of course, your values later on would be 0 and 1. Very clear, very specific, very simple. But as you look into dy later on, x's will reappear. So that's the idea for providing you with the appropriate region. Unlike the first two videos where the regions for x and y are very specific. Now, take note, this is just for the first part of the discussion. We are not yet on this process. Allow us to continue here as we solve for the partial derivative of your q function with respect to x. What is our q function? The q function is actually, by the way, I forgot to write it here. Let me move this down so that you will be guided with this. And this video might be very long, so pardon with that. Okay, so we will have here our q function, x and y, is actually this function with beside dy. That's actually x plus y squared. As for your p function, it's beside dx. That's 2xy minus x squared. Okay, that would be your your specific functions. So for the partial derivative of q with respect to x, it's the partial derivative of your x plus y squared with respect to x, stating that our y squared will now be treated as a constant. So when we talk about that, the partial derivative of that is obviously the derivative of your x, which is 1, and the derivative of your y squared, which is actually 0, treating that as a constant, giving us 1. Now, moving towards the second, which is this one here. So the partial derivative of your p function with respect to y is the partial derivative of your p function 2xy minus x squared with respect to y. Again, at this point, x would be treated as constant. This would be constant. That would be constant. So with respect to y, your derivative here is actually identified as, with respect to y, 2x. And this will become minus 0 or simply 2x. So that's hopefully clear for this one here. Now we have this 2. And again, we'll be rewriting this in terms of dy and dx. So your double integral here will be formed as, since we'll be writing dy first, so the outer boundary here would be for x. The boundary for x would be 0 and 1. But for your inner boundary for your inner integral is this one here, x squared square root of x. Upper boundary and lower boundary of your, this one here, that's 1 minus 2x. Right? That's 1 minus 2x. And then you will have here, again, we will start with dy and then dx. Okay. So hopefully that's clear. This is the understanding for this specific item here. So now let's try to solve this by starting with the inner integral here. Okay. So let's try to move that here and later on apply the outer integral. And take note, we are doing this with respect to our dy. So as we use here, treating this as constant, it's also constant because that's with respect to y. That would be linearity property. So you have here the integral of your dy from x squared to square root of x. And then minus 2x, treating that as constant. Similarly, the integral of your dy from x squared to square root of x. So you will have here, of course, that's y. Obviously, x squared square root of x minus 2x, y, again, x squared square root of x. But that is only for your y variable. So you will have here, as you use now your boundaries, upper boundary will be square root of x minus x squared. Okay, that's for your y, minus 2x. Take note, let's group that because it's preceded by negative sign. So you will have here times your upper boundary square root of x minus 2x, and you have here x squared. Okay, so hopefully it will be clear for this. Square root of x minus x squared, this will become minus 2x square root of x plus 2x cubed. If you don't want square roots, of course you will have the x to the power of 1/2 minus x squared, and you have here minus 2. That's of course x to the power of 3/2. That's 1 plus 1/2 and plus 2x cubed. Okay, that would be integrated here, because later on you will have now from 0 to 1 of this entire form here, x to the power of 1/2 minus x squared minus 2 x to the power of 3/2, and you have here plus 2x cubed. Okay, so that's dx. So that's it, and of course all of them are now in excess. So you will have to apply here the rules on integrals. So for this 0, 1 x to the power of 1/2 dx minus 0 to 1 x squared dx minus 2 linearity property. You will have here x 3/2 dx, and again plus linearity property x cubed dx. Allow me to copy this because I don't have much space here and add another page. Okay. Alright. Hopefully that's okay with you, because let's now apply the rules. Take note, we can actually have here integrals of u to the n du, but your n are no longer just integers. You also have fractions here, but still we'll have the same concept with that. So the integral of x to the power of 1/2 is obviously x to the power of plus 1, right? 3/2 over 3/2, 0 to 1. Then minus x cubed over 3, 0 to 1. Minus 2, take note, you have here 5/2 over 5/2 plus 2 x to the power of 4 over 4. Forgot right here. Sorry for this, because we still need to apply here 0 to 1, and again plus 2 x to the power of 4 over 4 is 0 to 1. Allow me to simplify those rational expressions. That's 2/3 x to the power of 3/2 is 0 to 1 minus x cubed over 3 is 0 to 1. This is 5/2, or that would become 2/5, so times 2, 4/5 x to the power of 5/2 is 0 to 1, and this one here, of course, obviously, plus x to the power of 4 over 2 is 0 to 1. Okay, step by step. You will have here 2/3 times 1 to the power of 3/2 minus 2/3 times 0 to the power of 3/2. That's for the first. Take note for the second term, it's negative, so grouping symbol. You will have here 1 cubed over 3 minus 0 cubed over 3. Next, still negative, so grouping symbol. 4/5, that's 5. 1, 5/2 minus 4/5, 0, 5/2, and plus, you will have here, you may not need grouping symbol because this is plus. You have here 1 power of 4 over 2 minus 0 to the power of 4 over 2. Remove all zeros, that's 0, 0, 0. So we have 2/3 times 1 is 2/3 minus 1/3, because that's 1/3. Next, minus 4/5, because you have here minus. But you are to add 1/2. So for LCD, I believe it's actually equal to 30. So you have here 20 minus 10 times 6 is minus 24 plus 15. That's actually 35 minus 34, 1. So you will have here a result of 1/30. So after all of this processes, very long process, our answer here is 1/30. That's the answer to the integral of this bounded by y is equal to x squared and y squared equal to x, using or verified using the Green's theorem in the plane. So the answer again is 1/30. Thank you very much for watching.